Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Emilie Dunham with us today. Hello, Emily.
Hi everyone, nice to be here.
Well, thanks for agreeing to talk about your very awesome article, which we'll get to here very shortly. And Emily, what is your geolocation? Where are you at?
I am currently in Livermore, California at Lawrence Livermore National Lab.
Bay Area.
Yep,
Yes. And how is winter in the Bay Area on this February 9th of 2026 as we record this?
definitely nicer than the East Coast. No snow. It's been like
No
60s and
darts, no
sunny
darts.
lately. I know, I feel like I'm bragging so much when I talk about the weather here.
I'm in Phoenix, and so we are actually starting to warm up into our spring today. It actually feels like a very springy kind of day today. It's beautiful out, and this is why all the snowbirds from Canada come down.
Mhm.
Of course, we do pay the price in the summer, but yeah, winter is very, very pleasant, and generally in the West Coast and in southern Arizona, very nice. Cool. That is an awesome isotope table over your right shoulder
Oh,
there.
thank you.
Yeah, I think
Yes,
somewhat related to what we're going to talk to here about in a bit.
yes, chart of the nuclides. Always good reference to have.
Oh, it's very good. And speaking of, Emily, what do you like to do for research?
Yeah, so I study ancient meteorite inclusions to learn about how the solar system formed. So I'll talk about calcium aluminum rich inclusions today, and that was the focus of my paper. And here at Lawrence Livermore, I mostly study pre-solar grains, which formed in stars before the solar system formed, and we
Cool.
use their isotopes to learn about how stars form.
Uh-huh. Uh-huh. And what that initial solar composition was. Mystery, mystery.
Hmm.
Very cool. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. The CII database, aluminum 26 and magnesium 26 isotope systematics. And Emily, take us away.
Okay. So before I talk about the paper, I will highlight my co-authors here. So I was joined by a few people from UCLA. So that's Ming-Cheng Liu and Kevin McKeegan.
Mm-hmm.
Kevin was my postdoc advisor at UCLA,
Mm-hmm.
and Ming-Cheng was, yeah, a big collaborator.
Very nice.
Um, and I'd also, yeah, like to highlight the Aman, Fatima, Danielle, and Ashley are four students that I got to work with.
Oh,
And
very cool. Okay.
yeah, because this was a database, it was a huge effort in compiling data. And that's, yeah, having students to help with that was very necessary.
Beautiful. And they got an article out of it, so very good.
Yes.
Good shout out. Good shout out. Okay, let's go ahead and get into it.
Okay. So, I guess first I'll talk about what CAIs are, just to give you
Okay.
guys an overview. So, that acronym stands for calcium aluminum rich inclusions, and they are small inclusions within meteorites, and they are about 2 to 10% of
Yeah.
meteorites. So they make up a pretty small proportion too, and they're well, something like 10 microns to some centimeters in
Yeah.
diameter. So there's quite a range of sizes. And CAIs are really awesome because they are the first formed solids in our solar system.
Okay.
So they form, or in the protoplanetary disk,
Hmm.
when things are really hot, there are no solids that can form. But once the temperature cools just enough, you can get solids that condense out of the gas.
Cool.
And the first minerals to form are those which are in CAI. So calcium and aluminum are very refractory elements, which means they become solid at very high temperatures.
Yes.
So that's why calcium aluminum rich inclusion.
There you go. That was
There
good.
you
Thank
go.
you.
Yeah, sure. And um, cosmochemists, which is what I am, we have studied CAIs since they were found in like the 1960s-ish.
Yeah, yeah. Mm-hmm.
And
Mm-hmm.
um, yeah, so CAIs, people have been uh, finding them using scanning electron microscopy,
Ah.
which is one of the main methods we used in this paper too.
Mm-hmm.
And yeah, so we find them with that, and that's how we understand their mineralogy. And that's one way to figure out uh, how, when, where they formed.
Yes.
But isotopes are another very important aspect to understanding uh, the environment in which they formed, and also when. So the reason that we know CAIs are so old is that they've been dated using uranium lead isotope systematics, so
Oh,
not aluminum magnesium,
right.
but so the uranium lead tells us that they formed 4.568 billion years ago. We
Yeah.
have pretty good uncertainties on that too, so it's
Good.
incredible to know their old age.
Yes.
Yes.
I believe it.
And yeah, so people have been measuring isotopes in CAIs for a long time, since the 1970s. Um, and I think it's been up until, well, there was a database compiled in 1995. That's the McPherson 1995
Oh,
paper I
yeah, yeah, yeah.
reference at the
Right.
top.
Mm-hmm.
And
Mm-hmm.
so that was a really um, big deal when that came out, because we finally got together a bunch of data and could see, get a better view,
Trends.
broad scale view of
Yeah.
what CAIs were telling us.
Mm-hmm.
So that paper, as well as some recent compilations, really inspired me to want to make a new database that
Cool.
was accessible. So the whole idea
Ah,
behind that is that we want to put all the data together in a way that other researchers can grab it and um, make their own conclusions, interpretations, figure out where there are gaps, how how can we um, get the best data possible with having this big scale view in mind
right. And get it out for people to use.
and for people to use. Yeah.
No more copying numbers off a printed page.
It was quite difficult to
Yes.
get the data out of those 1970s
I
papers.
bet it was.
So it's very useful to have it all now in one place. Um,
Beautiful. We're going to take a look at that when we get there.
totally. And the focus of this paper was
Yeah.
aluminum magnesium isotope systematics.
Okay.
So I hope to add more isotope data to the paper eventually in later releases, but um, aluminum magnesium isotope systematics is a really important data set to have for CAIs, because it tells us about their formation time and formation conditions.
Right. Hmm.
Mhm. So I'll describe that a little bit for people that might not know about aluminum magnesium. So
Okay.
aluminum 26 is considered a short-lived radionuclide. And by short, we mean in terms of the solar system timescale.
Right.
So it has a half-life of 0.7 million years.
Uh-huh.
And there are a number of ideas of how aluminum 26 was um, injected or inherited into the early solar system.
Yep.
But we know that it was there because we can see that there's an excess in the daughter product, magnesium 26.
Yes. Huh. Good.
Yeah, so even though aluminum 26 doesn't exist anymore, its half-life is so short, we can look at the excess of magnesium 26 to kind of backtrack and figure out how much aluminum 26 did exist
Right.
4.568 billion years ago.
Cool.
Yeah, so it's a really useful tool to kind of be a detective and look back in time using CAIs.
Yay.
And yeah,
Yeah. Mm-hmm.
okay, so Yeah, now that I've explained aluminum, magnesium, you can kind of see the importance um, of compiling all the data together.
Yeah.
And yeah, there are also some conundrums about aluminum 26 and its distribution within the early solar system.
Okay.
So that's another reason why we want to put all the data in one place. So some people think that all CAIs have about the same abundance of aluminum 26,
Okay.
whereas some people see that there are some populations of CAIs that have lower aluminum 26 than the normal value.
Right.
And we call this normal value the canonical value.
Okay.
And we'll see that in some of the plots later.
You will. Mm-hmm.
Yeah, so
Okay.
I think we'll, yeah, get up to the next column. So a
Okay.
part of
Okay.
the aluminum 26 system is that, so to determine the aluminum 26 over aluminum 27 ratio, that's
Mm-hmm.
the ratio that we're going for because it's telling us about the initial aluminum 26
Yes.
abundance. And people that measure isotopes always talk about isotopes in ratios because that is what our mass spectrometers measure, and that's what's easiest for us. So that's why everything's in a ratio.
Good. Okay.
Um, so in CAIs, aluminum 26 was live when they formed in the early solar system.
Okay.
And at that point, um, all the mineral grains within a CAI would have the same value of aluminum 26, but as in it was 100% aluminum 26 and 0% magnesium 26.
Yes. Okay. Mm-hmm.
But then once it started to decay, oh, I should say that each mineral will have a different amount of aluminum, just depending on what mineral it is. Like corundum is Al2O3, so that has a lot of aluminum in it, whereas spinel has some magnesium in the mineral formula also, so it will have
Yes.
less aluminum. And this matters because once it decays, excuse me,
You're gonna do the ratio, right?
once it decays, yeah, are your magnesium is going to increase, and this all goes into the York regression that I talk about in this paragraph.
Mm-hmm.
So it's a little bit hard to explain this sort of plot, and I don't think I have an example of it in the paper,
It's
but
okay.
that's okay. You can easily find one of these in the literature that I reference.
Yes.
But the York linear regression is a way in which we take our data. So we have aluminum 27 over magnesium 24. That's on the x-axis. And
Okay.
then on the y-axis is magnesium 26 over magnesium 24.
Okay.
And so the
Good.
y-axis is really the extra magnesium 26
Mm-hmm.
that we're finding in the CAIs, which is representative of the aluminum 26, the short-lived radionuclide. So for this plot, we have a few data points and we draw a linear regression through them.
Mm-hmm.
And the slope of the linear regression is equivalent to the 26 aluminum over 27 aluminum initial value. And that's what the number that we want.
Yes. Okay.
And a part of this regression is considering the MSWD, the mean square weighted deviation. And this is just this, it's the same thing as like a reduced chi-squared. It's basically um, how scattered are your data about the line.
Okay.
And some
Mm-hmm.
CAIs have a really good reduced chi-squared of 1. That's like the ideal value.
Yes.
But sometimes they have reduced chi-squareds that are a little bit more
Mm-hmm.
than one, which means their data are very scattered. And this
Mhm.
could have to do with the CAI being later melted.
Ooh,
So
right, right.
this can happen in the solar nebula. So if a CAI experiences a shock wave or something, there are a number of mechanisms that
Set the
could
clock.
heat a CAI.
Mm-hmm.
Um, so this heating could actually reset the aluminum 26 clock,
Yes.
and that can make the data more scattered.
Yes.
So I
Okay.
say all of this because the MSWD is an important parameter for us to know if we can trust the 26-27 aluminum ratio.
Uh-huh.
Like, does that actually mean something about the early solar system
Right.
timing, or is that telling us about a different process?
Fair. Okay.
Okay,
Mm-hmm.
so yeah, I think that's um, most of that paragraph.
Okay. Cool.
Um,
I'm with you.
Yeah, and also the next paragraph, that's about the thermal metamorphism I was talking about that can
Right.
disturb the aluminum 26.
Mm-hmm.
And
Mm-hmm.
so
Reset the clock.
yep,
Yep.
we
Yeah.
definitely track this value in the database
Right.
in order to um, give us, but also other people who are using the database, um,
You.
just the knowledge that they should trust the CAI aluminum 26 value, or maybe it means something different.
Yeah. So
Mhm.
keep your head up on interpretations. Mm-hmm.
Yes.
Mm-hmm. Okay.
Okay, yeah,
Cool.
so
I'm
we
with you.
can keep moving down, I think, to yeah, I can describe uh the second equation just a little bit.
Uh-huh.
So as I said, aluminum 26 can help us to understand the timeline of CAI formation, but
Mm.
it's only a relative chronometer. So
Yes.
that means we only can figure out the age difference between two CAIs. We don't know the exact age.
Absolutely. Yes. Mm-hmm.
Yeah, so that's what this equation it helps us do. It
Mm-hmm.
so um, I didn't yeah, in a lot of the plots I don't show this relative age, but it's pretty easy to calculate. And so usually for one of the CAIs, we use the normal canonical value that I talked about a little bit ago, and then our CAI of interest to see if it's how much younger or older it is from that.
Okay. If you want to change that normalization, feel free. Okay.
Yeah, so people who
Okay.
use the database could calculate that.
Cool.
Okay, and now
Maybe we should look at
get
that database.
yeah, sure. So the database comes from 75 peer-reviewed papers, which is why this list is so insanely long.
Awesome. That is a heck of a citation list.
Yeah.
Okay.
And also, I want to emphasize that, yes, this last point,
Absolutely.
that
Absolutely.
of course, it was a lot of work to compile the data, but it was way more work to actually take the data from.
Absolutely.
This is data since like 1970. So
Hmm. Hmm.
this has
It's
been a huge effort on the part of cosmochemists. So please cite the original papers.
kind of like just citing the review paper instead of the actual papers that did the work, you know?
Yeah,
Yeah. Fine to cite both, but definitely cite the originals.
definitely a good
Absolutely.
practice.
Okay.
Yeah, so then the database itself, this table just shows uh, the table up on the right. Yeah,
Uh-huh.
it
Yeah.
shows the different categories that are in the database, and we could go take a look at it later. But yeah, like I said, it has the aluminum 26-27 rate initial slope value.
Okay.
Um,
Sigma.
and
Mhm.
the delta 26 magnesium star is the intercept of the plot that I described.
Uh-huh.
And that's another factor that can be important in telling if the CAI was melted or not, or if it
Ah,
had if it experienced things later that reset the system.
yes.
Mhm.
Mm-hmm.
The MSWD down there, the CAI sizes, and then we have as many notes as possible about
Right.
the mineralogy, petrography, shape, because the papers that have the data usually include many paragraphs of descriptions about the CAIs.
Okay.
So we did our best to compile that in the database.
Uh-huh. And I want to point out that the full table is in machine readable form online, so do check that out.
Yeah, it is also on the website that we can look at later as
Okay.
a Google sheet. So
Mm-hmm. Cool.
it just makes it easier for new releases to come out.
Absolutely.
Mhm.
Because everybody knows by the time you publish something, it's already out of date.
I know. I've already found papers that I have
See?
to add in. So,
See? Yes, yes.
Mhm.
Hmm. Okay, I'm good. I'm with you. Hmm.
Great.
Hmm.
Um, and yeah, one quick other thing we could talk about delta 25 magnesium.
Okay.
So
All right.
26 is the daughter product.
Yes.
25 magnesium is a stable isotope
Yes.
that can tell us about a CAI being fractionated. So this
Hmm.
could also happen during melting or even if a CAI was evaporated, so
Okay.
like very hot.
Hmm.
So if it experiences something like this, then the lighter isotope of magnesium. So this is the delta 25 magnesium means 25 over 24. That's just
Yes.
kind of the shorthand times 1,000.
Yes, that's the
Mhm.
per mil percent sign that we
Yes, that's
earlier.
the per mil value.
Hmm? Yeah,
And the us cosmochemists use that a lot because it's just an easier way to read a
it's the
lot of
natural way.
numbers so you don't
Yes,
have too many sig figs. It's like
exactly.
yeah,
It's
that's the only reason we do that.
okay, and
Hmm.
we will come back to this
Hmm.
later.
Yeah, so we can keep going.
Okay, okay, and they come from a whole host of things. Hmm.
Yeah. So since I'm gonna talk about these in the plots, I'll quickly describe just the types of meteorites they come from. So
Hmm.
CAIs are found in most primitive meteorites.
Yes.
So this means meteorites that haven't been melted very much, as CA or meteorites that are come from parent bodies that were melted, the CAIs will ultimately be erased,
Yes.
melted away.
Uh-huh.
So
Cool.
carbonaceous chondrites and non-carbonaceous chondrites are where these come from. That's where the CV, CO, CK, CM, CR, all of
Hmm.
those guys.
Yes.
And one really interesting thing is that there are way more CAIs from carbonaceous chondrite meteorites.
Yeah.
And these are ones that form in the outer solar system,
Okay.
which is kind of weird because
Yeah.
CAIs initially were synthesized in the very inner solar system, but most of them are found in meteorites formed in the outer solar system. So this is kind of it's related, but it's a bit of a different topic. Um,
Yes. Yes.
so a lot of
They
people are
moved.
thinking about how those got to the outer
They
solar system.
moved.
They moved somehow.
Right. Somehow.
Yeah. So the non-carbonaceous chondrites, which is the ordinary and the enstatite, those have some CAIs, and I actually have a paper
Yeah.
about that from a few years ago.
Cool.
But it's like 0.01 volume percent is
Hmm.
the CAI
Okay.
abundance. So it's super low and they're more tiny, which tells us more about how the CAIs were dispersed
Yes.
within the protoplanetary disk.
Cool. All righty.
Yeah, and there are many different kinds of CAIs that
Hmm.
we detail in the database. And I guess the main two classifications are CAIs that have not been melted and CAIs that have been melted.
Okay.
So we have the unmelted ones are called fine-grained because they have small mineral grains.
Hmm.
And when things have small mineral grains that are stuck together kind of in a fluffy,
Matrix.
um, yeah, fluffy, accreted way,
Okay.
that means
Same thing.
that they haven't been
Right.
later processed. This
Okay.
was kind of how they originally formed. At least that's our thinking.
Hmm.
Whereas things like type A, type B, type C, those ones have big mineral grains that can form triple junctions. This just means that they were melted
Yes.
to decent temperatures.
Hmm.
Um, and that doesn't necessarily mean the aluminum magnesium
Got
uh,
it.
system was reset,
Right.
but it's more likely. So, yeah, I can talk about some plots later comparing these two main types.
Yeah. Cool. Good, good.
Okay, and
Mhm.
one other main group I can talk about is what in this paper we call anomalous CAIs,
Ooh,
and
those are always fun. Hmm.
they are really interesting because they tend to have low aluminum 26, initial aluminum 26. And they have some interesting acronyms, as you can see. We have the FUN type, which stands for fractionated and unidentified nuclear effects, platyhibonite crystals or plaques.
Hmm.
And so these have been a source of confusion for a long time because uh, most CAIs have the same value of aluminum, of initial aluminum 26, but these guys don't. So does that mean they formed before the normal CAIs? And
Fair.
that could imply that aluminum 26 was injected into the solar system by a supernova or Wolf-Rayet wind, some supernova variant. Um,
Yes.
or they're just a mix of the pre-solar component of the molecular cloud that was
Ooh, yeah, inherited. Okay.
inherited.
Hmm.
So yeah, the kind of injection and inherited scenarios are the main ones, but there are some other ideas too. So
Good.
I feel like I'm more in the inherited camp, but
Yeah.
also there's still like I think putting together the database was I felt like one of my efforts in um not solving this, but helping it along to
Yeah.
see maybe what more data we need
Mhm.
to solve it.
That's very modest of you. Yes.
Mhm.
Okay.
Okay, yeah. So I think that's it before we get into the
Okay.
results. I talked about
Okay.
most of this.
Okay. Let's go into results.
Okay. So the first section is about the distribution of aluminum 26 in CAIs. So I've
Indeed.
already introduced this, but
Right.
in order to actually use the aluminum 26 system as a chronometer or like as a timeline of early solar system
Uh-huh.
processes, we need to know that it was uniformly distributed. Because if the abundance of aluminum 26 kept changing, then you like that's not a good clock. To have a
No, it's
clock, you have
not.
to start somewhere where
Hmm.
you know the abundance is
Right.
some value that's the same. So yeah, this has been a debate that's been going on for a long time, since way
Wow.
before I entered the picture.
Yes.
Um, and CAIs uh, won't necessarily answer this question or not. but it's still an important thing to, I don't know, have in the back of your mind to
Yes.
say, like, yeah, we need to assume that things are uniform
Okay.
for this chronometer to work.
Yes. Should we want to use it as such? Yes.
Hmm.
Okay. Right
Yeah,
there.
so I talked a little bit about this Davis et al. 2022
Right.
compilation.
Mm-hmm.
And yeah, so, and I also mentioned this canonical value. So I
Yeah.
state that here, it's about 5 times 10 to the minus 5.
Mm-hmm.
And
That's where it comes from.
Davis also finds that most normal CAIs center on this value,
Okay.
whereas the anomalous ones cluster around 0. And so maybe now you could go up to the plot
Yes.
and we
Okay. Let's take a
can
look at figure one.
see, yeah, the one on the left
Let's
with
pull
the
it back a
purple
little
and the
bit.
blue.
Mm-hmm.
Um, yeah, great. So the x-axis is the 26/27 aluminum ratio times
Mm-hmm.
10 to the minus 5.
Yes.
So I'm also plotting two different categories of data, the purplish and the bluish.
Okay.
And the isochron values are kind of how I divided up the data in the database based on the MSWD or reduced chi-squared.
Okay.
So the isochron data are basically those that have good MSWD.
Yes.
So in my mind, those are the trustworthy ones that probably retained their initial early solar system 26 aluminum value.
Okay.
So
Mm-hmm.
there were out of the I think there were, oh yeah, 397
Right.
in the database. So 151 have good isochrons.
Good.
Um, and then we have the anomalous data. So
Mm-hmm.
these are just the isotopically anomalous ones. Um,
Yes.
that, yeah,
Wow.
so they've been measured for other systems usually,
Wow.
and that's what hints at their anomalous nature. And then we
Yeah.
can use that information to put them in the anomalous category. So it's not just aluminum 26 usually that we're looking at for these guys.
Right. Other isotopes are a little off too.
Yes.
Uh-huh.
Okay, so then for the isochron data, you can see in the histogram that and the gray line there is the canonical normal value.
Yes.
So most cluster around there, which is very expected. And the purple line is a kernel density
Mm.
distribution.
Okay.
And this does not take into account uncertainties in the data. So
Okay.
that's the probability density function does. But we spent a lot of time deciding which one to use because,
Kernel probability, right?
yeah, because of course you want to take uncertainties into consideration, but the data have been taken since from the 1970s to now.
Yeah.
And now the uncertainties are way better because our instrumentation is way better.
Right.
But also, it depends what minerals a CAI contains to how
Mm-hmm.
good your uncertainty is. So
Mm.
there are just too many factors that can mess with the uncertainty of
Yeah.
each data point. So we just decided to,
Lots
for
of,
now, do the kernel.
yeah. Very good.
And that goes along with the little box plot up there.
Yeah. What are these? Mm-hmm.
Yeah, these are box plots.
Okay.
So I
Mm-hmm.
think the main box shows like the 3/4 of the data.
Mm-hmm.
We have the whiskers
Yeah.
that go out to slightly more of the distribution, and then the dots are the outliers.
Yes. Yes. Okay. Cool.
Hmm.
Oh, look at that guy. Okay.
Yeah, so there are some outliers definitely.
Mm-hmm. Even over here. Wow. Yep. Okay.
So there are some isochron CAIs, which means they're They probably haven't been melted, but they do show a low 26 aluminum value. So don't
Hmm.
quite know how to explain those.
Right. Yes.
Um, yeah, and so you can also see the anomalous data in blue is the histogram. It's clustering around 0, maybe a little bit above 0. I think the average was like 0.2 times 10
Yeah.
to the minus
Good
5.
there. Okay.
So that also agrees with the Davis et al. Compilation and also the 1995 compilation of data. So
Person.
things haven't changed so much, but we've gotten a lot more data.
Okay.
So I think in a statistical viewpoint, things are looking up, and
Right.
it makes sense to have everything together again.
Absolutely. Puts on a little firmer ground.
Yeah.
Okay.
Okay, so
Okay.
we can
Go over to the right.
just quickly talk about the last group that I created, which is called the not isochron group.
Oh, great. Because I was going to ask, because those two didn't sum to 300 odd. So here we go.
Yes. So these are CAIs that have MSWDs that are more than 3.
Okay.
Um,
Okay.
and or CAIs where they only have 2 data points.
Mm-hmm.
And that means you have to infer the origin. We call these model isochrons. And this has to be done sometimes if you have a really small sample, or like there are a lot of circumstances in which you can't measure too many spots in a CAI.
Okay.
So like it's understandable that this has to happen a lot,
Okay.
especially in earlier data or in earlier papers where the instruments had much bigger spots.
Okay.
So that's been another good advancement in the past.
Mm-hmm.
Maybe 15 years, we've gotten smaller spots from our mass spectrometers.
Cool. Very cool.
And so you can see here, like there is a clustering around 5, there's a
Yeah.
clustering around 0,
Yep.
but like looking at the box plot, it's such a broader
Wow.
distribution. Like,
Absolutely.
so it was very satisfying to make this and see that the MSWD categorization actually worked and
Right.
shows
Yes.
um, that the distribution of the non-isochron data is very diffuse.
Yes. Good. 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 Good.
Mhm.
Put them
Yeah,
both up
so those
there.
are
Absorb. Okay.
yeah,
Cool. I'm with you.
excuse me. Great.
Mhm.
Okay, so I think we can keep moving down to the next um
Okay.
figure.
That's the histograms. We talked about that.
Mhm.
Normal. Oh, table two. You want to say anything?
Yeah, I'll mention a few things. Um, so the first
Here's the
um
three we just looked at. Yes. Mm-hmm.
Yeah, so the first figure was all about looking at the distribution of aluminum 26
Right.
and finding that most CAIs do have that 5 times 10 minus 5 value.
Mm-hmm.
But then wanted to look at the different CAI groups in more detail.
Okay.
So it's basically just breaking up the database
Mm-hmm.
uh, into groups that make sense
Populate.
from
Right.
a few
And
different
sizes.
standpoints.
And sizes.
Yep, we got sizes, we grouped it by meteorite type,
Mm-hmm.
grouped it by CAI type,
Cool.
bunch of different things.
Very nice. Okay.
And yeah, and then we had the median, standard deviation, and standard error.
Yep.
So we chose to do the median because the distributions aren't really Gaussian. So to do an average wasn't, I don't know, it didn't fit perfectly.
Appropriate. Right.
So that's why we did median. And then standard deviation shows you more about the range of the data
Mm-hmm.
within each group. Whereas the standard error, it takes into account how many data points are in each group.
Okay.
So it can show you, it's a way to compare each group to each other. So standard deviations like within the group and standard errors between the groups.
Good.
So we show both of these in different ways to kind of yeah, get a sense of differences or
Mm-hmm.
just to compare.
Mm-hmm. I'm good. I'm with you. Mm.
Okay, so the first thing we did is comparing the meteorite type of the CAI. So we can go to the next plot, I think, to
Yep.
do
There we go. Right
that.
there. Boop-a-doo-doo-doo.
Yes.
Yep. Uh-huh. Uh-huh. Good
So
for you too. Okay.
yeah. So the plot here shows the aluminum 26-27 ratio on the y-axis, and it's a Caltech plot, so it's just, or is that what everyone calls it? That's what I learned how to call it.
Okay. 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 I can understand why. Yeah.
Okay, I don't know the backstory behind that,
Okay.
but so it just ordered by value. And
Okay.
the data point colors show the
Okay.
different meteorite types. So in the circles is carbonaceous chondrites, and the squares is ordinary and anstatite chondrites.
There we go. Yeah. Just
And
ordered by value.
only
Doesn't matter
very
what they are. Right. Mm-hmm.
yeah, only very few of the ordinary and ancillary chondrites have been measured.
Okay.
So
Right.
yeah, because they're tiny and hard to find. And so the main takeaway
Okay.
from this plot
Yeah.
is that yeah, all of the groups have a bit of a range, but they do cluster again at 5 times 10 to the minus 5. That's that
Mhm.
dashed horizontal line.
Right. Cool.
Mhm. But then like the C is a C ungrouped, and these are just meteorites that don't have a group, but they're
Okay.
carbonaceous.
Okay.
So that like sometimes there are a few outliers, and
Yeah.
um, I like having a big plot like this so that people can see each individual CAI data point. So it's
Absolutely.
not grouped.
Very cool.
Um,
Right.
maybe not this one, but the next one we can look at the database.
Sure. You want to do the violin plot first?
Yeah, let's go to the violin plot.
Okay, let's blow that up. Okay, violins.
Yeah, so this is another way of showing that same data, so grouped by chondrite type,
Yes.
but we have the violins. So these are, yeah, I learned about these plots by writing this paper, through writing this paper, and I really like how they show the distribution of data.
Yeah.
So I've had fun with them. And yeah, so the violin part is actually a KDE. So the like left curve and the right curve show the distribution of the data. But
Mm-hmm.
then um within the violin is a little box plot where
Yes.
the like horizontal gray line is the median.
Mm-hmm.
So that is just a more specific
Mm-hmm.
way to describe the data. And then you can see the data points in there.
Right.
So they're kind of randomly oriented in the x-axis. So that's why they look a little bit scattered, but
Yeah.
it's just meant to show like where all of the data are falling
Very nice.
and where the outliers are.
Very nice. Uh-huh.
Yeah.
I like that.
Maybe we can check this one out on the website.
Sure. We're gonna pop over to the open website where you can get the data and play with it yourself. Okay, there we go.
Yeah, and there's a link in the caption.
Yes.
So this is the database that me and my co-authors made associated with the data. And the reason we want to do this is to just make it more interactive and have like a home for the database.
Mm-hmm.
So we can first go, so the, yes, continually in development.
Absolutely. Okay.
Yeah, and my student Fatima, she helped to figure out how to get plots on here that are interactive. So that
Very.
was great because I did not know how to do that.
Mm-hmm.
Yeah.
Okay.
So
What
if
would you
we
like
go
to
to the
do?
plot tab in
Mm-hmm.
the right corner and then go to violin/box,
Nice.
that will bring us to the violin plots.
Ah,
So that's the one that I just showed you.
yeah.
And what's cool about these is that they're interactive. So if you hover over it,
Ooh, wow.
each data point has like
Cool.
each data point will tell you more about it when you hover over it. So like it will tell you what paper it's from, the actual value, what kind of CAI it is, descriptions,
Cool.
which can be helpful if you're really needing to go in detail.
Absolutely. Very cool.
Another fun thing is you can zoom in. So if you just like draw a square, I think, you might have to click. Okay, cool.
Nope. Click the
Yep, so
button.
you can
There
go
you go.
look closer. Yeah, and then it gives you some details about the
Uh,
violin plot as well. Yeah. And I'd like to show one more interactive feature in that the box on the left that says data colon isochron with the
yes.
arrow.
Uh-huh.
So you can click on that and then you could try anomalous.
For example,
Oh, maybe you need to click on, there's a little home button on the right of that. Yeah, or a little house.
the little house. Little house.
Yeah.
There we
Okay,
are. Yeah, we had to
perfect.
reset the plot. Yeah. Okay.
Yeah, that's just to unzoom it.
Mm-hmm.
So now
Okay.
this is the isotopically anomalous data.
Nice. Okay. And it's
So
not in the
it
paper.
gives you a way
Okay.
to look at all the different subsets.
Mm-hmm.
Um,
Very nice.
yeah,
Very cool.
sure. We can go to this one next. It's
Yeah.
also in the paper, so we could
Okay.
just look at it here.
Let's do.
Okay. So I mentioned CAIs have a lot of different types. So these are comparing those using the violin plot feature.
Okay. Mm-hmm.
Um, what are some things that I could highlight? So we have the CTAs, or let's see. So the melted ones I mentioned are
Right.
the Bs, Cs, and CTAs.
Mm-hmm.
And so,
Zoom in on those.
yeah, sure.
Now that I'm an expert on zooming here. Yeah.
Yeah, so type Cs we know are very melted. They're kind of a highly evolved type of CAI. Even the minerals are more evolved. So it makes sense that they have a pretty extensive 26 value or
Mhm.
a big range.
Right. Mm-hmm.
But not too many have been measured. So
Yeah,
that's one
more.
thing people could measure more of,
Ooh, that.
maybe like 4 or 5.
Oh, look at that. If you just stay on the envelope telling you about the envelope. Very cool.
Yeah.
That's beautiful. All right. Mm-hmm.
And then like
Okay.
many more type Bs and CTAs have been measured, and
Mhm.
their median is slightly lower than the
Okay.
canonical value.
Yes.
Hmm.
Five here.
So
Yes.
that is something to note.
Okay.
Maybe if you zoom out again, do the home button
Uh-huh.
and um, I'll just mention the fine-grained FGI and FTA. Those are the unmelted ones, but I'm gonna show a plot later where we'll compare these two groups more because it's hard to really, yeah, compare things in this form.
Yeah. Okay. But very
Um,
nice.
and before this, do you mind going back down again quickly?
Nope, not at all.
Thank you. So the last couple groups,
Mm-hmm.
those are from non-CV type meteorites. So
Okay.
CV is the Vigorano type carbonaceous chondrite,
Mm-hmm.
and it's the main type where CAIs are studied because they're generally really big and easy to find. But the rest here, which don't have the same classification system of CAIs,
Hmm.
so I did my best with the
Mm-hmm.
papers that had this data to kind of group it by the main mineral type or the main mineral that constituted the CAI.
That makes sense.
So
Okay.
like we got grossite rich, hibonite rich, melolite rich, and spinel rich.
Okay.
And
Mm-hmm.
yeah, so that's the CAI type thing is something that could be worked on as well, I think, to merge multiple meteorite types together.
Huh.
But yeah, these ones, there aren't as many measured as you can see, but
Um,
and they generally have lower 26, 27 values.
a little bit,
I don't
a little
really
bit.
know why, but it could be
I don't
that they're
either.
smaller and harder to measure.
Mm,
Um, so there could be like multiple biases going on, and it's hard to uncover at this point. But now that the data is all together, maybe someone can help with that.
start figuring it out.
Yeah.
Very cool. Okay.
Yeah. So I
Great
think we can
website.
go back to the table or to the paper.
Yeah.
Oh yeah, we could show the
Just
table.
click on table. Okay. Ooh.
That's all the
Yikes.
way down at the bottom.
Okay. Ah, there we go. So this is also the online table.
Yes.
Yeah.
So this would be the if you download this as a CSV, it would be basically the same as what you would download from the paper. So they're just different or copies of in different forms.
Uh-huh. Good, good. I mean, a
Hmm.
variety of availability. Very
Yeah,
nice. Okay. Well, thanks for making that. I think that's very handy.
good.
Okay.
Yeah, I've been watching as the paper came out to see how many people have gone to the website, and
Ah,
it's
yeah,
been pretty
yeah,
fun.
yeah, yeah. Uh-huh.
It came in a big wave the day it was released.
Absolutely. Check out something new. Cool. Okay, so covered figure
Okay.
3,
Yeah.
and I think we covered this one as well
Mm-hmm.
on the website. All right, and so this one we did not cover. So let's summarize them by type.
Yeah, so this is basically putting everything together in one plot, which
Yes.
might be a little confusing, but
Okay.
um, it's the X or the Y-axis again is the 26-27 aluminum ratio. And
Mm-hmm.
then we have all the different ways to divide up the samples on the X-axis.
Right. And that was in table 2. Hmm.
Yeah. And right, this is everything from table 2. So
Right.
we have the median is the data points, standard error, the small red ones are um yeah, a way to compare from sample or from group to group. And the
Yeah.
standard deviation is more showing
Within
the
group.
distribution within each group.
Yes, I'm with you. Mm-hmm.
So, for
Ah.
example, if you look at the anomalous data, that's
Mm-hmm.
the third group
Mm-hmm.
over,
This one?
they have their standard deviations are pretty big.
Yes.
So that just shows, yeah, that maybe these CAIs are grouped in a way that,
Hmm.
like maybe they could go into further and further subgroups.
Yeah,
Because these are grouped based on other isotope data or
true.
there are, yeah, a few different reasons why these are grouped as they are. Um, but maybe each group has CAIs that have gone through different things,
Mm-hmm.
which is why, yeah, the
Mm-hmm.
distribution could be bigger.
Yeah,
So,
but globally, yeah, 10 to the minus 5-ish across all of them, pretty much, even size. Mm-hmm.
yeah, yeah, and this shows also that like the size CAI sizes don't matter too much.
Right.
Like small to big, they all have about the same value.
Mm-hmm.
Even petrologic type, they're pretty
Interesting.
much the same. And
Mm-hmm.
this was a little bit surprising to me because petrologic type tells you how melted a meteorite is.
Yeah,
So I would think like if the meteorite parent body was more heated, then that's more likely to have heated the CAI and
yeah,
made it a lower 26, 27 value.
right,
But
right.
that seems to not be the case.
Huh.
So,
Yes, we'll get that in the melt as well over here. Mm-hmm.
mm-hmm.
Mm, okay. Pretty darn uniform overall.
Yep, I think so too.
Mm-hmm. That's interesting. Yeah, well,
Okay.
okay, you're You're leading me into the inherited camp. Okay.
Yeah. Oh, have you been in the other camp?
Injection, right? Injection one
Injection.
way or another from a master's. Right, right. Okay, that's
Okay, so
Ellen.
now, yeah, we can keep going.
Yeah, that's okay. So that was five. Then we get into
Yeah,
direct
six would
melts.
be a good one to describe.
Okay.
So, as I've been talking about, we have the unmelted
Uh-huh.
CAIs and the melted ones.
Yep.
And so this is directly comparing those two groups.
Mm,
So there are like multiple different types in each of these groups. So the unmelted has the fine-grained inclusions, the fluffy type A's, and the melted has type B's and type compact type A's and type B's. I know the classification system is a bit of a jumble, but yes.
okay. Hmm.
Yes, um,
Ten.
so there's an idea that the unmelted, it's the relationship between the unmelted and melted inclusions has been a big question for a while in cosmochemistry. So like are do melted CAIs come from unmelted ones? Like are they directly correlated? Are they kind of the same thing?
Okay.
Or did they start as different groups and one of them was just melted?
Okay. Okay. Good.
Um,
Good.
so this is
Yeah.
trying to get towards the answer of that. We don't have an answer yet, but
Mm-hmm.
that's how science goes.
Mm-hmm.
So the purple here shows the unmelted.
Yeah.
So
Mm-hmm.
yeah, the histogram as well. So, and there's a bit of an overlap of the histograms, which is why there's like a weird color in between.
It's the opacity transparency.
Yes, yes.
Yeah, yeah.
So it does look like the unmelted ones are have a little bit of a higher 26-27 aluminum ratio
Right. Slight.
with the histogram and the KDE.
Uh-huh.
So, and the box plots up there, the line in the middle shows the median.
Right.
So you can see how they're shifted.
Yeah, there's a little bit of a shift.
Hmm. But then again, the unmelted category has a bit of a wider distribution that you can see from the box plot more easily.
Right.
Um,
Eh,
this is because there are
yeah, a little
some
bit.
data points that are a bit lower, 26-27 ratio.
Yeah. Yeah.
And yeah, those have been talked about, but I think the data look good. So
Okay. Okay.
that's not the problem with the data. So it's something that we'll need to explain.
Straighten out at some point. Okay.
Yeah. And another cool observation that came out of this plot was that the histogram is not very Gaussian. Like
No,
it
it's not.
kind of starts at a really high level and then at 5 point something, and
Drop
then it
off.
trickles off to the left.
Boom.
So it is
Mhm.
not
Mm.
symmetrical. Like it's
Right
not at all symmetrical,
here
which
too.
is why putting a KDE, representing it with a KDE is, I don't know, maybe a little iffy, but that's as good as we could do right now.
Mm. Yeah, there's definitely a drop off on the high side. Pretty sharp one too. Well,
Yeah,
you get a few oddballers out there, but yeah. Mhm.
yeah. And most of
Okay.
the oddballers out there
Okay.
have pretty big uncertainties
Okay.
and or other reasons why, yeah, they might not be completely trustworthy.
Okay.
Um,
Arguing for an
so
even more one-sided distribution.
yes.
Hmm.
And it seems like the melted has a pretty strong cutoff on that side too. It's
Yep.
not quite as strong, and I tried a number of different binning situations to see if that would
Mhm.
affect it, but it doesn't affect the unmelted.
Okay.
Um, and
Hmm.
so this tells us that the unmelted CAIs began forming at a pretty distinct time.
Yes. Yes.
They didn't have like a starting trickle and then it got formed more and more and more and then less and less and less. It was like boom, they all started forming.
Right. All at once. Boom.
Mhm. And I mean, it's hard to tell if it was all at once. but like it's yeah, within a pretty fine time period.
Window.
So I think
Hmm. Hmm.
I'm trying to remember the exact numbers I have in the paper, but it's like something like 50,000 years.
Okay.
Um,
Okay.
so
Mhm.
yeah, that was the main finding is that melted forms a little bit after unmelted. Um, oh yeah. Oh, so that's the time difference
Right.
between the KDE peak of the
Uh-huh.
unmelted versus the melted.
Yes.
So 40,000 years younger would be the melted ones. Um, but again, there's a lot of wiggle room in that because the distributions are wide. So I
Right.
think we'll still have to get some more data um,
Always.
to yeah, constrain that number a little bit better.
Okay.
Um, but yeah, that's the time difference, which is pretty small in the grand scheme of the solar system.
Compared to, the half-life, yes.
Yeah,
Okay.
compared to the
Or
half-life
even less than the
too.
solar system, right?
Hmm.
Absolutely. Okay.
So we don't know yet if that means if like if melted CAIs come from unmelted CAIs,
Yeah.
or if the second peak just represents a melting episode.
Mm-hmm.
We don't know if it seems like CAIs were melted over a number of different episodes, but maybe there's one big one.
Mm-hmm.
Um, oh,
Yeah.
and this talks about a few of the higher 26 ratios.
Yeah, that's good. Okay.
Yeah, so not we can't totally use those as super canonical ratios. They're not they're not very strong,
Right.
I would say.
And we did run a video with Ed Young not too long
Oh
ago.
yeah?
Yeah, you can go check that out. He was talking about thermodynamics, but yes. Mm-hmm.
Okay. That's great. Yeah, I've been on a few things with him.
Mm-hmm.
He's fun
Very
to work
cool.
with.
Yeah. Yes. Okay, let's slide down
Yeah.
a little bit. And we talked about, we looked at the sizes,
Yeah.
we looked at the melts, and
Yeah, so the last
these are the
thing
low
is
ones.
this aluminum 26, sorry, magnesium 26. And
Right.
so
Delta. Or
this
both.
is the initial, well, this is the intercept of each CAI isochron.
Uh-huh. Hmm.
And so if a CAI is not melted, it will generally have a value of 0. So that's why I have that dashed line
Yeah.
at 0.
Mm-hmm.
But if it has been melted, it would have a higher value. So this is just has to do with like the mechanics of drawing an isochron regression.
Mm-hmm.
And
Mm-hmm.
yes, but well, it could also mean if there are different 26 magnesium values, it could also mean that the CAIs condensed from gaseous reservoirs that had a different
Oh,
magnesium 26 value.
okay.
So
Yeah.
that would be interesting to know if we have CAIs forming in different environments.
Two different reservoirs. Yes.
Hmm. But yeah, it's
Okay.
difficult to tell if that happens or not. Or kind of like difficult to
That
tease out which of these could be the
you can
scenario.
find.
And usually people talk about delta 26 magnesium when they measure bulk CAIs using ICP-MS
Mm-hmm.
because this helps you get really small uncertainties. Um, and
Yeah.
as you can see, there are a lot of big uncertainties here, or these are just uh, I think these are the standard errors. They're
Right.
very wide.
Uh-huh. All of
Um,
anomalous categories,
yeah, so
not ice prone. Mm-hmm.
yeah,
Or not measured. Mm-hmm.
or not measured.
Yeah, there's blanks here. They're not measured in some of these. Okay.
Yep.
Okay.
So it's helpful to put this stuff in papers
Yeah.
for future people.
Mm-hmm.
But
Hmm.
uh, I was going to say that having the database allows us to put together a lot of 26 magnesium values, which reduces the standard error of the mean.
Yes.
So it's kind of like the ICP-MS data is better for individual CAIs,
Hmm.
but the SIMS data can still be useful if you have compile a bunch together.
Hmm.
That's kind of the idea. So I don't know if, yeah, not too many people have done this with SIMS data before, I think, just because it's not as good.
Okay.
But yeah, so maybe we can go down to
Okay.
the plot of
Certainties.
aluminum 26, 27 on the x-axis, and then we have the delta 26 on the y-axis.
Hmm.
And these are the data, individual data within each group.
Got it. CTA, B none. Okay.
Mhm.
I'm with you. So there's
So
correlation there. Okay. Hmm.
yeah, so the left plot is showing the unmelted CAIs,
Okay.
and the right plot is showing the melted ones.
Okay. Ooh. Yes.
So the unmelted ones, there is still a range, but most of the data is below zero,
Hmm.
whereas the melted ones, well, there's still a range.
Hmm.
It's generally above zero.
Generally, yes. That would, yes, that agrees with figure seven. Uh-huh.
Yes. So we wanted to show all of this
Okay.
data together because the
Okay.
whole range tells us that it probably wasn't different reservoirs that these formed in, or else they would have more distinct
We
values.
think so, yes.
Yeah.
Hmm.
So
Yeah.
the difference probably has to do with melting, like having the unmelted ones being a lower initial value, melted ones being higher. Um,
Uh-huh.
yeah, so that's kind of the idea, but we're still needing some more
Right.
data and just we need to look more into um, yeah, different aspects of CAIs to make a stronger claim for this. So this is
Okay.
kind of a wishy-washy claim for in this paper, but
You got to start somewhere.
yeah, but me and my co-author Francois Tissot, we're planning to do some more work on this topic. So
Very cool. That leads into the summary and open questions, and that might be a good time to move it.
yeah,
So, Emily, I want to thank you so much for walking us through your very awesome article and database. Very nice.
thank you for your interest. I was
Sure.
really happy to talk about it.
Sure. Let's see, and you kind of hinted at it a couple times as we went through, and certainly in the last section, there are some ideas put forth. But let me just ask, where do you think we go from here, given the published article and current database? Is there what would it take to get
Yeah.
10 times as many data points as what we have now? Are there specifics that one would go after within the different types, and so on? And is there some theoretical work that might be able to be done? So
hmm
where do you think we go from here, given the published article?
Yeah. I'm excited to keep adding more isotopes to the database. I
Hmm.
think that it's useful to correlate different systems to see where that goes because each isotope system means something different. And so to put them all together
Hmm.
would give us kind of an extra toolbox.
Yes.
But that will definitely take some modeling because to correlate even to correlate more than two isotope systems, you need to have multi-dimensional plots. So
Right, right.
yeah, I wouldn't be able to do that by myself for sure.
Okay.
Um,
Cool. There is.
and there are, yeah, many of other different types of CAIs that can be measured. Like, I've been working on a paper for a bit now, which is about aluminum magnesium in the NC-CAIs or
Huh?
the ordinary and enstatite chondrites. So
Mhm.
that will be good to add some more data because there have only been, yeah, a handful
Cool.
of
Yeah,
CAIs measured for those.
yeah. Nice.
So that is, in comparing to the database, it's going to be really cool to, well, it's been very useful for me in writing the paper to have the database. So
Yes.
I think that's a good experiment for it.
And others will find it useful as well too. So
Yeah,
yeah, very nice. Cool.
more CAIs and yeah, I work with theorists, but I am not a theorist, so I don't know I don't know specifics about how this can be used,
Okay.
but I think just having the data available in a hopefully understandable way can
Mhm.
open the door for, yeah, theorists to use it
There
for
you
disk
go.
modeling,
Yes.
timing of
Yes.
things. So disk
Yeah.
modeling is, yeah, probably the main,
Mhm.
a good first step.
Mhm. Cool. Very nice. Well, it'll be really exciting to see this develop over the next couple of years, both experimentally and theoretically modeling wise. So it'll be very nice to see. Very cool.
Mhm. Great.
Yeah, Emily, I want to thank you so much again for walking us through your very awesome article and database.
Thank you, Frank. This has been really fun.
Sure. And that'll do, everyone. And I hope this made your astronomy day just a little bit better and your cosmochemistry day a little better too. And we will see you on the next one. Bye bye.
Bye.